So far we have discussed sequential containers, associative containers, as well as unordered containers, right? Let us try to discuss the fourth part of the container, which is adaptive containers. Right, as we discussed earlier, adaptive containers are just a wrapper which are built on top of other primitive containers, and they provide us a new kind of functionality in order to fulfill a particular requirement. Right, so adaptive containers we are dividing into three parts: stack, queue, and priority queue. Right, so these are the three adaptive containers which we plan to discuss. Let us discuss stack first. So the container stack here in C++ follows the property of last in first out. Okay, so just like a stack only, we will have multiple elements here. We'll keep on pushing them just like this. Let's suppose the elements which are coming in this order is 1 2 3 4 5. So 1 will come here, 2 will come here, 3 will come here, 4 will come here, and 5 will come here. And when we try to get out the element, 5 will get out first. So the last one which is getting in is the first one which is getting out. So in stack, like we can define a stack like this. And there are multiple properties of a stack. The first thing is stack.top. Stack.top will be O of 1 here. Why? Because it is getting me the topmost element of the stack. We can also pop an element from stack. So the pop will also be O of 1 here in this case. Right? So stack is like very simple. All the properties of stack will get followed in this container. The other container which we plan to discuss is queue. Okay, queue also, as the name suggests, follows the property of first in first out. Okay, what does it mean? Let's suppose if I have a lot of numbers which are coming in this direction, 1 2 3 4 5 6, and they will go in the same order, 1 2 3 4 5 and 6, but the order in which they will get out will be different, right? So the first one which is getting in will be the first one to get out, not the last one, just like in stack, right? So here the property which we follow is we can define a queue container just like this, and the front element q dot front here will be O of 1, because we can get the last element here in O of 1. We can also do q dot pop. It will actually pop the frontmost element, and there are all the other properties of queue will get followed up here as well. Right, we'll see more functions here in queue in the code coming up. The third one which we plan to discuss is basically my priority queue. Now this is the important one, since we are going to use priority queues a lot, mainly in heaps and graph based algorithms. But how we can define it? It's more like an abstract data type, wherein the ordering of the elements could be defined by the user itself. We will see how we can define the order in priority queue when we discuss heaps and graph algorithms. The basic implementation here is, I mistakenly made it double. It's actually simple at single element only. The basic implementation here, like the most default one, would be of max heap. Okay, so if I do something like this, it will define a max heap for me. Now those of you who don't know heap right now, leave it. We'll discuss heaps in the next sessions, few upcoming sessions. But it will actually be helping us in implementing max heap. Right? Again, like we can push element using push only. So max q dot push 1, max q dot push 2, and keep on doing this, right? We can also pop the element, max q dot pop. It will actually pop out the topmost element, and we can also use the top element just to get the topmost element, right? So size is also available in max q, priority queue. So these are just the APIs of different functions we can write in priority queues. This will remove, this will actually access to top element. Cool. So that's about the definition of all of these three adaptive containers. Let us now look at the code implementation of these three. the adaptive containers. So mainly we will be discussing stack queue and priority queues. Okay, let's start with stack then. So stack is one of the most like primary data structure which we use. In general, all of us know what does it do. So it basically help us identify the elements, and whatever elements it going last will be the first one to get out, right? So it follows the property of LIFO, which is last in first out. So it basically helped me do LIFO here, wherein the last element which is going inside the stack will be the first one to get out, right? So yeah, we can push elements inside the stack. Like let's just try to push some elements. So 56 will go in, and let's just copy paste the same here. Let's just try to push some more elements. So 36, 87, and let's try to 198. So we'll push these elements. Now to pop back elements one by one, instead of using the iterator approach, we will use a popping back mechanism. So we will do, while stack is empty, we will try to first of all print the element. So this will be accessible by stack.top. So stack.top will actually give me the topmost element, and then we can do stack.pop. So this will pop out the last element, right? So this will help me print all the values inside the stack. Let's also write down the size of the stack now after these operations are done. So yeah, let's try to run this. So if you see, the first one to get out is the first one to get in is the last one to get out. Okay, so last one to get in is the first one to get out in another way. So 198 is actually printing first, and 87, then 36, then 56, right? So this is the same order in which we are pushing the elements, like exactly not same like the reverse order in which we are pushing the elements, we are popping it down out. Okay, so that's about stack. Now let us look at the another one, which is queue. Let's just write. So queue, just like stack, is similar kind of data structure, only differentiation is it follows FIFO, first in first out property. So queue we can define similarly here. So queue dot insert, queue dot push, sorry, let's just push few elements here. Okay, so we have pushed 4 elements in the queue. Let's just try to pop them out. Similar process will get followed up here. While queue is not empty, we'll keep popping them out, and first we'll just print the element. So queue is queue dot front. So that's one difference. We need to print the front element, so queue dot front instead of top element. And then what we can do, queue dot pop. So queue dot pop will actually pop out the element. Also let's try to print the size of this queue towards the end. Okay, this will print the size of the queue. Let's try to run this now. Okay, so if you see, the order in which they are printed is the same order in which they are pushed. So queue is first in first out, right? So the third one which we plan to discuss is priority queues. Priority queue is more like an abstract data type. It does not follow any order, but the default one is actually based upon max heap. So defining a priority queue, something like this, max queue. So this, the default one, is actually an implementation of max heap. Okay, if you don't know max heap by now, it's fine, we'll discuss it later. So priority queue also follow the same process. We can push some elements. Let's suppose if I push few elements, 54, 65, sorry, it is queue here, and let me also push some more elements, 8, okay. So we have 4 elements which are pushed inside priority queue. Let's try to print them. While max queue is empty, we'll keep on printing the elements. So cout max queue dot top will give me the topmost element inside priority queue, and then I will do max queue dot pop. So this will pop out the element. Let's also try to print the size here. Okay, so let's try to run this. Okay, there's a typo here. Let me just fix the typo. XQ it is. Okay, so if you see here, the elements are actually getting printed in a maxi fashion. Like the largest will get printed first, and the second largest is 65, then 54, then 8. Right? So that's how we can push them. There is another way we can actually reverse the order here. So that's basically a min queue. Min queue definition is something like this. So we can define it like this, and give a container name in which you want to push the elements and a greater function. So this will actually help me print the min queue. Let me just try to run this here. Let's just implement here only in this case. So if I want to make it a min queue, print them in reverse order, I'll just define it like this, which will define a min queue here. So if you see, the order has been reversed. So this is the min heap. Okay, min heap, wherein all the first element, which is the smallest one, will get printed first. So a priority queue can be actually it's a very flexible abstract data structure. We can use it in multiple other formats. If you want to print the elements in some other order, we can actually modify this greater function and write our own logic. We are going to use it a lot while discussing heaps, but for now, yeah, this is the implementation of the trivial priority queue.